During the Cold War, the United States built a spy plane so fast it could outrun missiles. To do it, engineers needed a metal that wouldn't melt at 3 times the speed of sound. There was only one option, and the country that supplied most of it was the Soviet Union, the very nation the plane was built to spy on. That metal was titanium, and that story is just the beginning of what it can do. What makes titanium different? Titanium doesn't have one exceptional property. It has several, and they happen to be exactly the ones that matter in the 2 most unforgiving environments humans operate in: the deep ocean and outer space. Titanium's high strength-to-weight ratio is crucial for components in airplanes, spacecraft, military armor, and medical implants. That ratio, roughly equivalent to steel at 40 to 45% of the weight, is what every aerospace and naval engineer is looking for. Titanium forms a thin, stable oxide layer on its surface when exposed to oxygen, which makes it effectively immune to corrosion in seawater, unlike steel, which begins degrading almost immediately. The U.S. Geological Survey lists titanium among the critical minerals essential to U.S. national security, and specifically calls out its use in airplanes, spacecraft, and military vehicle armor. More than 95% of titanium used in the U.S. during 2024 was imported from other countries. The metal that holds American spacecraft together is almost entirely sourced abroad. The submarine. In the 1960s, Soviet engineers decided to build the fastest attack submarine ever attempted. A steel hull couldn't survive the combination of depth and speed they were targeting, so they chose titanium. The Papa-class K-222 prototype, completed in 1972, hit a top submerged speed of 41.2 knots, roughly 47 miles per hour underwater, and a test depth of 400 meters. The Alpha-class production boats matched the speed and operated routinely at depths beyond 700 meters. The Mike-class Komsomolets reportedly achieved a test depth of 1,000 meters. 3 reasons made titanium the only viable choice. The titanium hulls could withstand fatigue and fractures just as strong as steel at 33 to 50% of the weight, and able to withstand the high pressure of a deep dive. Titanium is also paramagnetic, a condition which reduced the magnetic field and helped the submarine become less detectable. It is also less corrosive in seawater. The problem was making it. Titanium melts at about 1,668 degrees Celsius, significantly higher than most metals, and reacts instantly with oxygen at high temperatures. When hot, even a trace of air can ruin a weld. To construct pressure hull sections, Soviet yards had to create sealed, pressurized workshops where the atmosphere could be tightly controlled. The U.S. Navy watched what the Soviets were building and ultimately concluded titanium submarines were not worth the trouble. The manufacturing cost was simply too high. That decision, steel and stealth over titanium and speed, defined the different strategic philosophies of the 2 Cold War navies. The spy plane. The same properties that made titanium essential underwater made it irreplaceable at altitude. The SR-71 Blackbird was designed to fly faster than any missile that could chase it above Mach 3, where aerodynamic friction heats the aircraft skin to temperatures that destroy aluminum airframes. The design team chose to make the jet's external skin of titanium alloy, which shielded the internal aluminum airframe. According to former Blackbird pilot Colonel Rich Graham, the airplane is 92% titanium inside and out. Then came the supply problem. The world's largest supplier of titanium ore was the Soviet Union, America's adversary. The CIA set up shell companies to purchase the ore from the very nation they were building a plane to spy on. The Soviets sold it. The Americans built the plane. It flew over Soviet territory for years. They never intercepted it. Spacecraft. Beyond the atmosphere, the same logic holds, and the stakes are higher because you can't bring anything back for repairs. The Ti6L4V alloy is widely preferred for spacecraft structural components due to its outstanding mechanical properties. Titanium inserts serve as critical mounting points, securing devices to spacecraft and satellites while handling heavy loads at minimal weight. Titanium also mitigates thermoelastic stress, the expansion and contraction that occurs as a spacecraft moves between direct sunlight and shadow, where temperature swings can exceed 300 degrees Celsius. On the Martian surface right now, NASA's Perseverance rover is storing rock core samples in titanium sample collection tubes, chosen because they must remain uncontaminated and intact for a potential future retrieval mission. The samples that may eventually tell us whether life ever existed on Mars are sitting in titanium. NASA research identified titanium as the candidate metal for multi-wall thermal protection panels on re-entry vehicles, in the temperature range up to 675 degrees Celsius. Coming home from orbit is as demanding as leaving. Here is what connects a Soviet submarine diving past 1,000 meters, a spy plane flying at Mach 3, and a rover on Mars. All three are operating in places where the environment will destroy almost everything you send into it. Pressure that crushes steel, heat that melts aluminum, corrosion that eats through most metals within years, temperature swings that crack weaker materials within months. Titanium doesn't solve all of those problems perfectly. It is difficult to weld, expensive to source, and hard to machine. The Soviets built entire pressurized workshops just to work with it. The Americans had to buy it covertly from an adversary. None of that stopped either country from using it, because when the environment is that extreme, the cost of the right material is always lower than the cost of the wrong one.